All right, so we're jumping back in the middle of section 2.2. We're looking at describing sets, and we are going to be taking a look at a visual representation on how we can do that called Venn diagrams. You very likely have seen Venn diagrams used before. I was teaching it's a Wednesday night class at our church to 5th and 6th graders, and something in the curriculum that I was using, completely unrelated to mathematics, was using Venn diagrams. And the 6th grader that was in the classroom knew exactly what this was. He's not a public school kid, but I remember my daughter in 2nd grade is the first time she saw Venn diagrams. So these are used, and not only in mathematics, but they are a diagram used to illustrate ideas in logic, which is why you see them used in more than just math. A universal set is the set that contains all elements that are being considered in a discussion. And the complement is always based on what some other set is. So if we're given a set F, and it's all, then the complement is all the elements in the universal set that are not in F. And your book uses this notation. They use a F, because it's referencing back to set F, with a bar on the top. Okay? If you've had contemporary math, which I know at least Tessa had contemporary math with me last semester, that's not the notation of that particular resource. That particular resource uses a prime notation on the end of it. That's another common notation for complements. Another common notation is actually like a C, kind of looks like a subscript or like, a power of C. That one's actually the best one probably because it's got C complements sort of built into it, but it's not used quite as frequently. Okay, and I'm going to draw you a picture of the complement once we actually draw pictures of what Venn diagrams look like. So, actually, I've got space on this slide, so I think I'll do it down here at the bottom. So let me draw a picture of a Venn diagram. Okay, why isn't that deleting it? Let's try this instead. Okay, so a Venn diagram is drawn as a rectangle. Okay, and the sets inside of it are drawn as circles. So draw yourself a circle or an oval or something inside. We label the outside as U. So the rectangle, sort of surrounding the circle, is the universal set U. And the part that's inside the circle is what we're calling our set F. So if I were to shade set F, it'd be all the part inside here, right, that region of it. And if I were to talk about F complement, it'd be everything that's inside the rectangle but outside of F. So this piece right here that's in red is the complement piece right here. Okay? So it's the donut, right? Where that's the donut hole in the middle. Yeah? It's that space outside there. So that's what complement's looking for. All right, so taking a look, and we can use a verbal description for our first one. So let's let U be the set of all students at OBU, kind of a picture in mind what that is. And A is the set of those who are graduating. What would the complement of A be in that situation? Don't overthink this. What's the complement of A? Okay, so it doesn't have to be seniors necessarily, but the ones who are graduating, probably most of them are seniors, right? I mean, they're probably almost seniors if they're not seniors. Do you have an idea, Madison? Right. And we still need to specify that we're still talking about OBU students, okay? So A complement would be all OBU students. And it's exactly what Madison said, it's who are not graduating. So in many ways, complements kind of go hand in hand with negations, which is what we've been working with in section 1, right? The opposite of something. It's still within the confines of the description of things in general that we're looking at, in this case OBU students, so we can't go outside that, picture. But it is the complement or the opposite or the negation of the other piece, that is students that are graduating versus students who are not. And we also have something called a subset. So a subset is simply a smaller collection inside the set you already have. So for all sets A and B is a subset of A, if and only if every element of B is an element of A. I'll draw you a picture in just a second, but first the notation for subsets looks like this. So it says B is a subset of A. So it kind of looks like a U on its side, or like a really squished C. In fact, sometimes we will read this that B is contained in A. So that kind of has that C kind of feel to it. In terms of a picture, actually, I think I'm going to flip back to my other one because I can draw it better. Well, I don't have a lot of space. Do I have any space over here? Not much. Okay, let's go back over here. Here's some space. So draw yourself that same rectangle that you had before with the same circle inside. I'm going to label my circles a bit differently because they gave me letters that were different. But what this is actually representing is like a circle inside of a circle. That's what subsets are. So if B is a subset of A, then it means that the B is inside the inner circle and the A is the outer circle, and all of it is residing inside of the universal set. So it's some sort of a way of categorizing something that's a little bit more specific, right? So perhaps, again, we had like the U, right, is all the OBU students, and the set A is actually those who are graduating, but the set B is freshmen. Does that make sense? Right? So I didn't say that very well. I'm going to stop back. Let me write it down because that was not a good example, actually. Scratch that completely. Let me write it down. Let's do our U as our universal set, and it's all of our OBU students. What I meant to say is that A is those who are not graduating. Therefore, then B could be the freshmen. That's what I meant to say. Okay? So the freshmen are a category that's inside of everybody who's not graduating, and the ones who would be graduating would be this outer donut area that we talked about before, the complement, the way that this is sort of being set up. Okay? But it's just a category inside of a bigger category. Now, that's a subset. A proper subset is the following. So for all sets A and B, A is a proper subset, B is a proper subset of A. If and only if B is a subset, that makes sense, right? Proper is an adjective describing subset. So it has to be a subset first. And there's at least one element of A that is not in B. And the way that this is written, hang on just a second. Yeah, that's right. I want to make sure I didn't have something typoed wrong. It's correct. The way that this is written is it looks just like that notation before, but it doesn't have the equals underneath it. So literally what this is meaning, without that line underneath it, is that they can't be the same thing. But on the first one, they could be. Okay, so let's just imagine for a moment, back to my example. We'll come back to this number of subsets in a second. Just imagine for a moment that all of the OBU students who are not graduating are already freshmen, right? We don't have any juniors or seniors for some odd reason. They just don't exist at all, okay? Well, if that were the case, then this A and this B would be describing the same group of people, but just in different ways. Those who are not graduating, those who are freshmen. They'd just be two descriptions meaning the same group of people, okay? Technically, it'd be a subset, because everything in the freshman circle is also in the circle of people that are not graduating, right? It'd be a subset, but they're actually just descriptions that mean the same thing, okay? So that's a possibility for subsets. It's not a possibility if there's proper subsets. Proper subsets means that it really is a smaller thing. It really is a category inside of something a little bit bigger. You cannot have the equals, and therefore you don't see the equal notation underneath it, okay? And we can actually find how many subsets of things that there are using some real simple formulas. So if we have n elements, then there are 2 to the power n subsets. And there are 2 to the n minus 1, just one fewer proper subsets. I think I've got an example. Yeah, I do. So we'll look at an example here in a second. So once you find one of these, right, you're usually asked to find subsets first. All you have to do to find proper subsets is take one away. So if your number of subsets were, say, 16, then the number of proper subsets would be 15, right? It's just one less. Okay, does that make sense? Okay, so taking a look then, we're going to consider all of the math faculty members. We actually have 5 math faculty members right now. If we wanted to create some sort of a group, we would have lots of ways of creating groups of us, right? Smaller collections of the whole 5 of us. And this question is asking you how many different subsets are there, okay? So the way that we find that is we take the number 2 and we raise it to a power, and the power that we raise it to is the number of elements. How many math people are there? 5. So this is 2 to the power of 5. So what is 2 to the 5th? If you don't know, grab a calculator. Do you know what it is? It is 32. Yes, very good. It's 32. So if there's 32 subsets, which there are, that's correct. How many proper subsets are there? 31. It's just 1 fewer. Okay? Now, if we wanted to change this and we wanted to make some sort of a subcategory, and we wanted to talk about just the female math faculty members, there's not 5 of us because we're not all female. There's only 3 of us. And we could do the same thing. How many subsets would there be? Will it be 2 to the 3rd? What's 2 to the 3rd? It's 8. And how many proper subsets would there be? 7. It's just 1 fewer. Okay, so whatever description we're working with, but this number can get big really quick. I mean, 2 to the 5th, 5 is not very many elements, and 2 to the 5th is already 32. If you do 2 to the 7th, you're at 128. Okay, so the number gets pretty big pretty quickly because it's an exponential that we're talking about here. So we do have numbers that can be quite large. There we go. Okay, so not only can we take a number of elements like we just did on that problem and figure out how many subsets there are, we can also take the number of subsets or proper subsets and figure out how many elements there are. So let's suppose that we have a set about which we know that there are 63 proper subsets. How many elements would there be in the set? So let's think backwards, right? This is a working backwards example kind of problem. If I have 63 proper subsets, how many subsets do I have? 64, okay? I'm adding 1 back in because I took 1 out when I created proper subsets. There's 64 subsets. So the question then would be, what number do I have to raise? Like, what's the power I need to raise the number 2 to in order to get 64? Do you know? It's 6. So this is supposed to be 64. It's 6. So my question mark, which you're welcome to put a variable in that spot or whatever, is the number 6 because 2 to the 6th is 64. So the answer would be 6 elements. Okay, we're not trying to solve it by traditional means. I'm not trying to, like the way you would actually solve this problem is using logarithms. That's not the point. We're not using logarithms for the elementary school kids, right? But it's trial and error, right? If you didn't know what this number should be, if like Madison, she had it spot on, it's 2 to the 6th, that's fantastic. But if you didn't know, you'd just do something by trial and error. You'd say, okay, well, maybe it's 5, and you'd go 2 to the 5th, and you go, no, that's too small. I need a bigger power. Okay, let's jump and say, maybe it's 7, 2 to the 7th. Oh my goodness, it's 128. That one was too big. It's the number in between. Okay, it's got to be a whole number because n is representing a number of people in this context. I can't have half of a people, right? Like, it doesn't work that way. So I'm going to be using whole numbers, and I can trial and error that just fine. Does that make sense? Okay. So we have talked about these symbols before. I believe we did this last time. Do you remember what these symbols mean? Let's just talk about the first one, that E1. I mean, what does it mean? What's that? Not equivalent. Good guess. We did use the word equivalent, but it wasn't in this context. Does somebody else have another idea? Sorry. An element. An element. So this E means is an element of. And then the one with the line through it means is not. Okay, so it's either is or it is not an element of it. Okay, so there's a couple of things that can kind of go wrong. So when we talk about something being an element of something else, the first thing we probably need to check and make sure is it an element at all? If it's not an element at all, then it doesn't make any sense to talk about it being an element of anything else because it's just not an element, right? So taking a look at the first one, what's on the left-hand side? What does that symbol mean? It does mean no solution, but in set theory, we had a different notation that meant. Do you remember? Okay, let me go back. Let me find it in our notes. Is it here? Yep, there it is. Okay, what does it say at the bottom that this notation means? It's an empty set. It's a set that has nothing in it. Okay? But for the point of what we're talking about right now, it's an empty what? Set. It's not an element. It's a set. Are you guys with me? So on the problem that we're working on, and we're trying to find out, do I use an element symbol or a non-element symbol in that blank? It's not an element. And the reason it's not an element of what follows is because it's not an element of anything. It's a set. And a set is a collection of things. Okay? So over here, if I'm putting something in the blank, it's not an element of it because it's not an element at all. Okay, is everybody good with that? Okay, so that's our first sort of mental check when we're looking at something is it even an element at all? If it is, I can continue in the discussion. If it isn't, then I'm done and I know what the answer is. Second one then, what's on the left? It's a 15. Is it a set? It's not a set. How do I know it's not a set? Because it doesn't have curly braces around it. Sets are designated inside of curly braces, and the 15 that's written on the left-hand side doesn't have that. So at least I stand a chance at this being an element of what follows because it's at least an element. Okay, everybody tracking with me? Okay, so what follows then is a description on the right-hand side of some other things. It's not a list. It could be a list like we have it on D, right? This is a list of things. It could have been a list of things, but it's just not. So we need to figure out what it is describing when it gives us that set notation on the right-hand side of part B. What is this thing? Well, it says that it's the set of all x such that x is equal to 2n. Okay, well, what's n? N's the natural numbers. Natural numbers are counting numbers. It's the one that children start counting with. So we have to be able to put the numbers in that are our counting numbers, the number 1, the number 2, the number 3, the number 4. So let's see what this does when we actually accomplish that, or try to accomplish at least some of those. So if I'm taking a list of these and I'm actually writing down, well, what are these guys? If I put the number 1 in for n, what is 2 times 1? It's 2. And then if I put the number 2 in for n, what is 2 times 2? 4. Right? I'm putting the numbers in right here. If I put the number 3 in, and I'm just going by the counting numbers because that's what the natural numbers are. If I put the number 3 in, what do I get? 6. Let's go one more. If I put the number 4 in, what am I going to get? 8. Can somebody give me a description of what kind of numbers this is creating? These are even numbers. Okay, is everybody good with that so far? That's what that 2 is doing. It's creating even numbers. So we're back to the discussion. Yes, 15 is an element. But is 15 an element of the set that's being described on the right? It is not, because 15 is odd. It's not even, right? So this one is not an element of, but it's failing for a completely different reason than the first one did. Are y'all with me? Okay. The third one, C. What do you see on the left? Say it louder, Holly. What is it? It's a set on the left, right? It's a set. So is it an element? No. Sets and elements are different things. Now it's a set of only one thing, so it looks kind of funny. Right? It's a set of just one thing, but it is a set. And how do I know it's a set? Has the curly braces around it, right? So this one is not an element, but it's not an element for the exact same reason that A was not an element. The thing that's on the left, that quantity on the left, is not an element at all. It doesn't matter what comes next. It's not an element. So it's not an element of what comes next. Okay, number D. That's not a number, letter D. All right, what do we have on the left? Set or element? It's an element. How do we know it's an element? Doesn't have curly braces. Okay, what do we see described on the right? Even numbers again, right? This one's in a listing method. We don't have to do much to work with to see this. It's even numbers. So we have the number 16 on the left. We have the even numbers being described on the right. Is 16 an element of the even numbers on the right? Yes. So what do I get to put in that blank? I get to put the element symbol in that blank. So only one here that was an element. Okay, so you can fail to be an element for two reasons. Number one, you fail to be an element at all. And number two, you fail to be an element that's in the collection of things that are over there, right? Two things to check. Now, the next slide is going to look just like this slide with one difference, and the difference is in the directions. The directions don't tell us to put element or not an element in the blank. They ask us to put what in the blank? What were those notations talking about? You remember? We did them today. What is this one? We didn't talk about this one, but I think you'll be able to figure it out once we've established the first one. Not complement. Nope, that was when we had the bar on the top. What was it? Subset. So subset is this notation. It means it's contained inside of something else, right? A smaller grouping or a smaller description of something inside something bigger. What's the second notation going to mean then? Not subset. We didn't actually talk about that one, but you push a line through anything and it's still going to be a not, right? So this is not a subset. Now, inherent in the word subset is the word set. So something can be a subset only if it's a set. Is everybody with me? Do you see anything listed in parts A through D that's not a set? You should. Can you give me one, Allie? B. How do we know that what's on B, the 15, is not a set? Doesn't have curly braces. So if it's not a set, then it's not a subset. Y'all with me? Okay, so this one right here on B is definitely, hang on, let me get the symbol a little higher. Not a subset, because it's not a set to talk about. I mean, it's not a set at all. Any others? D, for the exact same reason, right? It doesn't matter what happens on the right. If it's not a set, which it's not, it can't be a subset. Okay, A and C, however, are sets. How do we know they're sets? Let's talk about C. It's the easier one. Why do we know C is a set? Curly braces, right? We see the curly braces. How do we know A, the zero with the line through it, is a set? What is the zero with the line through it? It's the name of it. It's the empty set or the null set, right? So it's a set by definition. Okay, so both of those are at least sets. Now that it is a set, we have to decide if everything in what is on the left is also on the right. Okay, the first one's a little bit wonky feeling, but walk with me through this. It's the empty set. What's in it? Not zero. Nothing. The empty set is a set that has nothing in it. This is going to sound funny. So is everything that's in the empty set, which is nothing, also in the set on the right? It is, because there's nothing that we have to consider to be included, which means everything by sort of default gets to be included. So I'd encourage you to write yourself a little note that says an empty set is always a subset of the other set. Not only is it always a subset, but it's a proper subset as well, because it's smaller. There's nothing in it, and there's something in the set on the right, it's number 0. So it's actually a proper subset. Those aren't questions that we were asked to deal with here, right? It's just subset, not subset, but it is a proper subset to be sure as well. Okay, the third one's more interesting in terms of it actually having details. Did you have a question? No, you're good? Okay.
Yeah.
All right, the third one's more interesting in terms of actually saying, does it work or not? So on the left, we have a set. How do we know we have a set? Curly braces, good. What's in the set on the left? The number 4. It's not very exciting, right? One little piece in there. It's okay. What's in the set on the right? Well, it looks funny the way it's written, but you can probably change how it's written into a way that's a little bit easier to see, right? I mean, we don't really need to write 1 plus 2. We could write 3. What else is there? 4, 5, and 6. So feel free to change the way the notation's written to make it more comfortable to look at if you've got something like that. But here's the question you ask yourself is, okay, we've got a set on the left. The set has the number 4 in it. So that's the only number I have to consider. Is that element 4 in the set on the left also in the set on the right? And the answer is yes, that it is. So since it passes that test of asking that question, it is a subset because number 1's a set, and number 2, everything that's in it on the left is also on the right. Okay? So it's different questions that we're asking, whether we're on this slide or on this slide, right? We're asking, is it an element? We're asking, is it a set? We're asking, is it contained in? That part's the same. Is that thing also in what's on the right? But that's the secondary question to ask. You first need to establish, am I even looking at something that's in a set or an element to start with, okay? All right, fundamental counting principle. The fundamental counting principle, so if you have had contemporary math or proportional and statistical, this does come up, so it's going to look a little familiar. And if you haven't, you still probably have seen this argument before. It says the following: if an event M can occur in the little m ways, an event N can occur in little n ways, then the events following, right, M following N, or M followed by N, can occur in mn ways. In other words, what you're seeing here is you're multiplying outcomes. And we're doing an example with clothes. Clothes is good, right? Sure, we're gonna do an example with clothes. So let's say you go to your closet, and because you're you want it to match. So assume that your closet matches. One of my daughters never matches her clothes. It's a frustration point when I look at her every time. We're gonna assume that it matches so that you're not going to, look weird. It says how many different outfits can be created from 3 shirts, 4 skirts, and 5 pairs of shoes. Okay? So what the fundamental principle of counting says is that I have to make 3 choices. Oh, good grief. It moved for me. That wasn't supposed to do. I have 3 choices to make. I have to choose a shirt. And how many shirts do I have to choose from? 3. I have to choose a skirt. And how many skirts do I have to choose from? 4. And I have to choose a pair of shoes. And how many shoes do I have to choose from? 5. And I can find out the total number of different, arrangements of outfits by simply multiplying these numbers together. So what is 3 times 4 times 5? 60. It's 60. There would be 60 outfits. Now, that's not saying they all look super different from one another, but there are 60 different ways that you could put your outfit together. Okay? So the fundamental principle of counting comes into play. So for those of you who had proportional and statistical with me, which would be JC and Allie. Madison, did you have that one with me? Jazzy too? No, not that one, a different one? Okay. Tessa, did you have proportional and statistical with me? No? Okay. I'm trying to remember who did. Emily, Kate did? Yeah, okay. So we saw this happening in probability when we were looking at probability, just as a reference point where you would have possibly seen it before. Tessa, you saw it in contemporary math though with me, right? Yeah, okay. So we see this happening here in numbers of ways we arrange things. One of the examples I use I think it's in contemporary math, is going to a restaurant and making choices, like meal deals people have, where you choose like your main entree and then you choose your side and you choose your drink kind of thing. And there's nothing special with 3 items. You can choose more than that and have things work this way too. Okay, so we're gonna go to the mall because we just talked about clothes. You have 6 favorite stores in the mall. In how many ways can the following happen? Well, the first one says you only have time to go to 3 of them. So once again, we're sort of assuming that we don't care if we backtrack. Practically speaking, you might not do that if you were shopping, but for the sake of what we're looking at here, that's the argument, okay? You're going to 3 stores in any sort of order. And so we have time to go to 3 stores. And we have maybe 6 that we want to go to, or maybe that we need to go to, but we only have time for 3. This happens when I run errands sometimes. I'm like, I only have time to go 2 places and I need to go to 5 of them. I guess it's these 2 today, right? So how many choices do I have to go to if I'm making my first choice? How many options? I have 6 options, right? 6 places that I'd like to go or need to go perhaps. But once I go there, I'm not going back. It's not like, this happens though sometimes at Walmart, you go in for something, you forget something, you have to go back in. We're not going back in the store. Okay, so we're assuming we're leaving and we're done with that store for the day. So you leave that store. How many choices do you have for store number 2? 5. and then you leave that store. And how many choices do you have for store number 3? 4. We saw this happen also when we looked at one-to-one correspondences last time, and the example I gave you was pairing people off to go on a date or something like that, right? We saw this 6 times 5. I think we did number 6 actually all the way down too. So if I do 6 times 5 times 4, what answer do I get? So there are 120 ways that this could happen. 120 different selections and arrangements of stores. But what if I have time to go to all 6 of them? Well, if there's 6 of them, it just means I have 6 blanks that I'm filling in instead. And what's going to go in my blanks? Yeah, I'm going to do this all the way down. We have seen this number, 6, 5, 4, 3, 2, 1. Does anybody remember or multiply quickly what that was? 720. There are 720 ways we can go to our favorite 6 stores. Okay, there's one last thing we're going to do today. And this will be our last thing because we don't have time to do group work, so we'll discuss that in a second. But what I want you to do first is I want you to create a real life example of the null set in your life. Okay, so I'm going to do one for you. This is specific to my life. It might not fit for yours, though for many of you it probably will. This would be the infants living in my home. And it's a set, so I'm going to put it in curly braces. It's a curly brace. There are no infants living in my home. You saw my picture, right? I don't have any babies. My baby's my grandbaby. She doesn't live there. She can stay with her parents. That's fantastic. I got to visit her this weekend. It was wonderful, but I got to leave her there, right? I can sleep at night. They can't. Okay, infants living in my home. There's none. This is an empty set. I want you to write one down for your life. What is an empty set in your life or a null set in your life? So take about, 30 seconds, a minute, write one down. I want somebody to be brave and to tell us what's the empty set you wrote down.
Cats living in my home.
Cats living in your home. Yeah, see, that wouldn't be empty set in mine because I've got 2 cats. It's a good example. Something else. Addison? Okay, so how many times doesn't work, but you could say something inside of there, trips to 6 Flags or something like that. We don't want to say how many because that's talking about cardinality. Okay, but you've got the right idea. Do you have one?
Chickens living in my coop.
Chickens in your coop. Did the chickens all get ate or
Yeah, they did.
dead chickens? So sorry. Anybody else? I usually have somebody in this class who says, boyfriend's in my life right now. Did anybody write that down? Not this class. That's okay. It's all good. Okay, does that make sense? You're describing something that's simply not true about your life. Are we good? Okay. So let me stop this.